Ladies and gentlemen, welcome to the House of Switzerland. It is truly a pleasure to welcome you here together in our space. My name is Dr. Chris Lubkeman, and I have the privilege of being the head of the Strategic Foresight team within the Office of the President at the ETH in Zurich. We are coming to you live from the pop-up house in Stuttgart. And thank you so much here for joining us in presence and online. Today, our fascinating panel is entitled, It's a Small World After All. Before we get started, I'm going to show you a little film. And there we go. Oops, I forgot that I have the thingy. Oopsie. There we go. Nope. Voila. Rethinking living is a theme which we in the ETH are going to be using for the next few years as we truly rethink what does living mean, all the way from the scale at cities and at a global scale, modeling our entire Earth, all the way down to a micro nano scale. And today we're going to the other extreme, which is this small world after all. I am honored today to host this conversation with two amazing scientists. Simon Schüle-Finke of the Responsive Biomedical Systems Lab at ETH Zurich and Hakan Ceylan of the Physical Intelligence Department at the Max Planck Institute for Intelligent Systems here in Stuttgart. So, Simone, come on up here. Simone is researching in the field of biomedical engineering, and she is assistant professor for responsive biomedical systems. She graduated in 2009 from the Karlsruhe Institute of Technology in Industrial Engineering and Management, and we actually came through Karlsruhe on the way here, and you said, this is where I went to school, right? Specializing in micro and nano systems. She received her PhD in microbiology from ETH Zurich and research at MIT on nanosensors for cancer diagnostics and methods for increasing drug transport. So welcome. Great to have you here.
Thank you.
Here we go. Thank you. And our second guest is Hakan Ceylan. Come on up. And Hakan is a senior research scientist at the Max Planck Institute for Intelligent Systems, and his research focuses on medical microrobots, bio-inspired materials, and intelligence at microscopic length scales. Now, they both are working on many of the same typologies, but we're going to be seeing a bit different kind of viewpoints from this today, right?
Yeah.
Yep. Okay. Now, you received your BSc in molecular biology and genetics and your PhD in material science and nanotech 2010, 2014 respectively from Bilkent University in Ankara. Is that correct?
Yes, that is true.
Did I miss anything there?
No, that's great.
Did I miss anything with you? I mean, come on, you guys have CVs like this long, right? But you can all Google them. So, welcome to both of you, and welcome Hakan. Let's give him a hand. There we go. Here we go.
Thank you.
Now, before you go anywhere, our time together is going to be around 60 minutes. All right? At first, Simone's going to give a short burst, and then Hakan's going to burst. I'm going to start asking a few questions, and hopefully you here in presence or you online will have some questions that you will also want to be asking online. You ping them to us, and they will be fed into me. And we'll start that dialogue together, and we're going to talk about where the future is going to go, and it looks like it's a small future. Ha ha ha. Ready? Oh, come on. Here we go. Okay, so let's start with a small world after all. Hakan, let's come on down here. I'm going to give you this.
Thank you.
Okay.
Yeah, good afternoon. It's really my great pleasure to tell you a little bit about engineering, actually living and synthetic microrobots to fight cancer. Some of you might know this movie, The Fantastic Voyage, from the 60s, where a small team of agents in a submarine gets shrunk and injected into their colleague's bloodstream to rescue him from a blood clot. Well, it is really far-fetched to shrink people, but wouldn't it be indeed fantastic if we could engineer tiny robots that could roam through the body to detect and treat disease? Well, we need to think about how small these robots would need to be. So at least as small as a red blood cell to basically still fit through the smallest junctions in our vasculature, so around a few micrometers. Now, if we want to then enter a cell and interact on a DNA level, we reach the nanoscale. And to give you a little bit of an idea of how small that is, you may want to imagine that the ratio of the size of DNA to a human is 1 billionth, which is about the same ratio as a human to the sun. So, well, it needs to be really small, and all we need to do now is make a large robot really small, right? Seems easy, and that is what actually many people imagine. So this is a Google search result for a nanorobot. But this is really not how it works at a nanoscale. And that deals basically with the fact that we need to rethink our engineering principles, because such tiny robots encounter much higher surface forces in relation to their volume than their bigger counterparts. And we can easily imagine this and understand this if we think about a cube of 1 meter length. If we fill that with a bunch of nanocubes, we end up with 1 billion times the surface. So basically, this will, of course, impact also how we can move through fluids and move, for example, through the blood. So this can be understood with the Reynolds number. Really, I want to bring this in. So there was Osborne Reynolds who basically phrased this dimensionless number or determined this dimensionless number, the Reynolds number, which describes the ratio of inertial forces to viscous forces. Now we get very small, the inertial forces get very small, which means this Reynolds number gets also very small. And that really impacts now of how we can move basically the fluid dynamics and the fluid regime at the small scale. And that can, so imagine basically if you are in a water tank and if you become now very small, your Reynolds number becomes very small, or you're in the same liquid, and it will feel as it would be very sticky and viscous around you as these surface forces become dominant. So let me show this to you. So this is a famous experiment from Jeffrey Taylor. It's old, but it really shows well the point. So if you put, let me play this again. If you put a fish with a fairly large Reynolds number into a water tank, it moves by flapping its fins, like symmetrically, and it can move well forward. If that fish would become now very small, it would feel like it's in honey or in a very viscous solution. And the same motion, flapping symmetrically its fins, would not move it any further. So how can we move at a very small scale? Well, it turns out that nature has, of course, a solution for that, because when we look at small microorganisms like bacteria, we see that they evolved at different swimming styles. So not symmetric, but a non-reciprocal motion, like they have a helical tail that is propelled by a powerful molecular motor, and that is how they move forward. So we thought, well, this is really smart, and many scientists thought that. So can we not copy this motion? So like these E. coli bacteria here, having such a helical tail, we basically fabricated tiny helical tails and made them magnetic. Because it's hard to engineer a tiny motor, so by having basically external magnetic fields that rotate, we can now propel these helices in their corkscrew-like motion, like we just saw, and they can move forward, like you see here, quite effectively through this fluid. And so we thought, can we now use such a tiny helix to better bring drugs to cancerous sites? And instead of now loading up that helix with nano drugs, we basically just wanted to look into how they potentially affect the motion and fluid dynamics in the vasculature and impact on basically drug-loaded nanocarriers to get them better into tumor sites. And so these are some movies here that show how such a propeller can flow against the stream and really impact these here model systems for a nanodrug around them to better push it out into the tissue, because that's really hard. And so we, basically our idea was, all right, let's use such a little propeller as an intravascular little micropump to push out nanodrugs. And it's always good before you do tedious experiments to do some simulations. So we looked into this like with a computational fluid dynamics model where we basically looked into the impact from coming from a vessel into the tissue. And we were encouraged by these computational results, and then basically built such a model where we have here a tissue model that mimics the cancerous tissue, highly comprised with lots of collagen, and here we have the vessel and this little propeller, and we basically measured then the amount of little nano carriers it could push into this tissue model. And we could see that it could significantly enhance the transport, and in that sense, take these nanoparticles or nano drug carriers on a fantastic voyage. While it's been exciting to work with the system, we also realized, and as a scientist we should be very critical, that it has its limitations. We wanted to be better than that, and for that we thought we would need more of these propellers, but then it gets very tricky to control all of them in these small vessels. They also start to interact with each other, agglomerate, like, you know, from fridge magnets. Basically the magnetic attraction can get an issue, and we don't want to form clots, so lots of problems. And we thought, well, these bacteria we see that I showed you before, they move so nicely, could we not just use real bacteria? But then how can we control them? Because we wanted to basically still have our magnetic control. Well, it turns out nature also has a solution for that, and there exist actually real bacteria that respond to magnetic fields. They synthesize these pristine iron oxide nano chains, basically little magnetic nanoparticles in their body, and use it to navigate with the Earth magnetic field. And so we can, of course, also control them by basically by exposing them to external magnetic fields, and then override their direction and guide where they should go. And what's really exciting is if you mix them now with, again, such nano drug carriers as a model system, you can, and these are here depicted in red, you can generate very large volumetric flows and move these basically control where these nanoparticles go through the control of these bacteria that generate these fluid dynamics and can basically direct them. And so in the same model system, we then also studied the effect of such whole swarms of these bacteria on the drug transport, and could see that they could actually impact quite tremendously that transport into these tissue models. And sorry about that. So now you might think this sounds a bit crazy to use real bacteria in the human body, like we're having bacteria in the bloodstream sounds like that is sepsis, and that is right. But there is this, but actually the idea, and we'll come to that, how this is feasible now and is really moving forward, this idea is actually quite old. So there was the immunopioneer William Coley, actually a bone surgeon, who discovered in patients with cancer who also had a bacterial infection, a regression of their tumors. And that deals, and back then this was not known, but this dealt basically with the fact that this bacteria can then recruit immune cells, and it's basically a form of immune therapy. And in that sense, while he had success in some patients that he deliberately then injected with bacteria, also bacterial inactivated bacteria that he injected, this approach was basically died down just because of also the rise of chemotherapy and radiation therapy, and also of some cases that did not end very well. But today we see a rise again in publications around the topic, and it deals with the fact that we have now new toolkits, and that is synthetic biology, that we can now engineer basically safer attenuated forms of bacteria that can be injected into the body and in the bloodstream, and can better control basically the response of the immune system to have it right where we want it at the cancer site. And we exploit here really, it's basically a renaissance of an old concept, and we exploit here wonderful intelligence of microorganisms in that sense. They in some sense are autonomous, that they can they amplify actually at the tumor site because that is a good condition for them to grow. They provoke the immune response, and they can also have basically onboard drug production because of some toxins that they can release. Now and thinking about also that our body has actually more bacteria than human cells, it might actually really not be so far-fetched to think about engineering and controlling now some of the cells in our body for therapeutic purposes. And that is also the rise of genetically programmable therapies that is more and more coming as we have these toolkits of synthetic biology. Now, as an engineer, I'm coming here again in with my group where we want to work now, or where we're working now with bacteria but control them with magnetic fields. And we showed here, we want to empower basically bacterial cancer therapy with magnetism. So use these traits of immunostimulation, we can add to them certain drug cargoes, attach them to their surface, but then also in addition control them with magnetic fields. And here we recently showed in now more elaborated models of tumors. So these are basically small tumor models. These are cancerous cells that form basically small clumps. And we studied the penetration of these bacteria into these tumor models under our approach of applying these rotational magnetic fields that can be scaled to human size. They are much weaker than the magnetic field in an MRI and can be really clinically translated. Now, we showed here this enhanced transport and penetration through this approach, but you can also imagine that as a living entity, there's much more than just bringing drugs there. They basically also need nutrients to grow, and we want them to grow in the tumor and basically bring their, in that sense, fight the cancer cells. And one fact that is interesting about these bacteria is that to produce these magnetic chains, they basically need iron, and that is what a cancer cell also needs. And there has been some therapy of trying to deprive cancer cells from iron. Now, but it has some a high systemic burden, because then your whole body is deprived of iron. Now, with this local growth of the bacteria and uptake of iron, we hope to basically take away iron just from the cancer cells. So these bacteria are here so that they're starved and basically die because of iron starvation. And we showed in our model systems that indeed we can induce a cell death by increasing ratio of these bacteria when we grow them together with cancer cells. And with that, I come to the end of this talk, and I hope I could give you a bit of an idea that we really entered now the age of living machines. So coming from bacteria-inspired robots to using real bacteria as living robots to fight cancer, among many other diseases. And with that, I would like to thank you for your attention and my whole team for the work.
Thank you very much, Simone. I'm going to suggest that, is the mic on? Mic on? Okay. So I'm going to suggest that we go right over to Hakan, because I have like a lot of questions for you. And I don't want to get to the end of the hour before Hakan has a chance to share what he's doing.
Absolutely.
Really, really cool. So thank you very much. And Hakan, come on up. You've got the clicker. And I think you've got the next slide. Yeah. And
I've got everything.
There you go.
Thank you very much.
All right.
Good evening, and thank you very much for coming today. So what you see here is an electron microscopy image of a macrophage. So it's a giant cell of the immune system that works by basically engulfing and annihilating any foreign intruders into the body. So here it has intercepted and internalized, intercepts and internalizes a helical type of microtumor that Simone has just mentioned that works by rolling like a bacterial helix, bacterial flagella does. So the thing is that, so when we load them with drug and send it, deploy it into the patient, what happens is that, so the cells of the immune system recognizes these robots as non-self and will try to eliminate it. So of course we cannot let that happen, and so we need to understand the dynamics between the dynamics between the microrobots and the immune system. So macrophages are the most critical cells in the first line of defense. So if these cells fail to tackle with these intruders, they recruit eventually the area T and B lymphocytes, which dramatically escalate the immune response. So when I mean dramatically escalate, I'm sure you have this feeling after you have this COVID vaccine. I guess everyone is vaccinated here. So you know the feeling, right? So it's an accelerated, so enhanced immune response that you would observe. So, but in order not let that happen, so we need to first understand the elucidated dynamics between the microtumors and the macrophages by exploring the impact of various physical and chemical parameters on the immunogenicity. So what we observe is that macrophage, so that is the morphology of these microsumers indeed has an impact on the immunogenicity, so on the way they interact with the macrophages. So the macrophages eat some of these, so they have all the same dimensions, so volumes and everything, but only their morphology is different. But somehow macrophages differentiate them and eat them some more and some other less. So this is a great way to design some of the robots such that they will be less recognized by the immune system. But as Simone has mentioned already, that so the motion at this small size scale also depends on the parameters on morphology. So that means that while on one hand we are trying to evade from the detection of this immune surveillance, but on the other hand we are indeed compromising from the performance of the mobility. So as a supplementary approach, we took a materials approach where we fabricated our microrobots from materials that can be harvested from patients themselves. So that means that we collect blood, for instance, from the patient, and then we created some formulations, simple formulations. All the ingredients are all clinically available and allowed to use, and then we are simply able to 3D print these microrobots, and we printed various types of microrobots. So this synthetic approach is great because with 1 milliliter of blood we are basically able to print more than 10 million robots with the technology that we have at the moment at our hand. So and the materials that they come from patient also exhibit some responsive behaviors. That means that the robots that we make can respond to the changes in the pathophysiological environment. So although these synthetic approaches are great to alleviate some of the problems that we are having in terms of the immunogenicity, but these are eventually complex materials, no matter what high portion we use from the patients themselves. So we cannot really fully evade the immune response. So that means that, but the idea of collecting material from the patients is a good idea because these are eventually self-materials. So in that sense, we explored the potential of live cells that are harvested from the patients, and these cells are indeed available. So there are many clinically precious cells, stem cells, immune cells that are used for many therapies, and then collecting them from the patient, expanding them in the lab, and then engineering them. So we call it enhancement, enhancing with different physical, chemical, and biological means, so that these cells can be steered by means of external magnetic fields, so they can be imaged under various medical imaging modalities, and we can use the tools from the synthetic biology to introduce synthetic receptors, so that cells can recognize some cancer cells, for example, and then they specifically synthesize a drug that we know kills that cancer cell. So type of enhancement can make all of a sudden a live cell robot, because it's a very analogous to this concept of cyborg, where a live being is enhanced with some machines, and here a live cell is being enhanced so that it functions like a robot does. And it is quite advantageous because all of the synthetic robots that we make, so we eventually load them with some amount of drugs, but it's finite, and we infuse it, and we need to, once the drug is consumed, we need to reload and administer it again. But when you have a live cell, so once you localize it to a certain position, so certain body site, then this cell will use the raw material from the environment and will continue to synthesize drug until the pathology is consumed. And so this is an example of how cell can be made to move. So what we do is that we basically develop a micromagnet and then attach it on the surface of a cell. It firmly attaches on the surface such that so when we apply the magnetic field in a rotating way, so this magnetic torque is converted into a surface locomotion type of motion. So we can control the direction, but the idea is that so at the tissue and organ level, of course, it's not possible to. I mean, it's not imaginable to use one or few cells, but we need swarms of cells comprising from millions of cells. So we are also after developing ideas, just the concepts how we can make the swarms of cell borks. They can make a realistic impact at the size scale of tissues and organs, while at the same time we are steering all of them under imaging guidance. Yeah, thank you very much for your kind attention. And if there's any question, I'm happy to take.
Thank you. All right.
Yep.
Thank you.
Sure.
So both you guys come on up. Come on up. Hakan, you're going to grab in the middle. And we're over there. So I've learned one thing already. I'm going to have to go back and watch the fantastic voyage. Because as an inspiration, you had it in yours as well, I think.
Yeah,
right?
sure.
In the top right, so you both had it. So there you go.
It's a great movie. So.
Yeah. And how many of you have seen Fantastic Voyage, the movie? Yeah, like a long time ago, right? So we're all going to have to go watch it again. Swarming. Both of you talked about swarming. And on one hand, I get excited when I saw some of the images you made. On the other hand, it kind of freaked me out. Thinking of the swarm, there's a book about that. And so how close are we to actually being able to use these potential therapies in our bodies? Like a year, 10 years, 20 years, like fusion is always 20 years away, you know. How soon? So Simone?
So yeah, it depends. When we start, for example, with bacteria as a living therapeutic, we have actually right now clinical trials going on and what will probably enter first really clinics is intratumoral injection. So when a tumor is well reachable or fairly well reachable, that you don't do a systemic injection, because that is still regarding the fine balance with immune response that is desired versus an immune response that would be done negative. And so, but this is as well, there are clinical trials as well going on. I'm saying just that actually the intratumoral injection is now already possible. And I believe that as we're moving further with really a convergence of tools from synthetic biology, but also engineering, so as we're working on better controllability with magnetic fields, so we're trying to basically reduce the number of bacteria you need to inject, because we have more effective ways to get to the tumor site and get it better into the tumor tissue by so basically empowering them, and so that can help for maybe just one example. So what is now used in clinics is actually E. coli bacteria, so the bacteria from our gut. And then they can be engineered in attenuated forms, but then they're not very aggressive because they're our good bacteria in our body. And in that sense, we can give them more power by attaching their magnetic material and then drive them with magnetic fields. So, sorry, long, yeah.
No, I love the passion. I mean, absolutely. But I do want to ask you, so. When will I be able to go to the apotheke and say, I'm not feeling so good here, and they're going to shove something into me?
I mean, technology-wise, that can be doable in the next, I mean, within the next decade, but I don't know in terms of regulation. So this would be possible, right? So we have seen already in the vaccination case. So the approval regulations, it's difficult.
Okay, so it's not the right. I'm not asking the right question. But I have a different question before I come to you guys. So I'm trying to understand about the delivery to the tumor. Let's say I have a tumor someplace. I don't know. Say I have a tumor in my arm, whatever. Very easily accessible. With I'm going to call them corkscrews, if I may. Sorry. Do they actually deliver? What are they delivering to the tumor? How do they attack the tumor? I didn't quite get it. I mean, cool pictures. I just didn't quite get what's actually happening to my tumor. Because you're starving it.
I mean, my idea is to eventually use cells. So if I come to some physical vicinity, they will know their way. So this is the idea. But in her case, I guess. So
if you're using the synthetic ones, the little propellers, then they would be, so if you just inject your drugs, only you can pack them in little nanocarriers, but only about 1% of the injected dose goes to the tumor, and it's diffusion limited. right? So they basically would enhance their transport into the tumor. So the drugs you already taken, but they have a little helper to pump it out from the vessels.
Okay, so the needle goes in, and as you said, there's little nano droplets. I'm not a doctor, right? So this is not my world. So there's little there's a fluid which has a bunch of nanoparticles, and you're attaching basically a propeller to the nanoparticles.
They can be attached, but you can also, if you just have them combined, and this propeller is basically pushing them out, so you use them as a little pump.
Okay, because that was the one you were showing where they're pumping them in.
Yeah, but then you
Got
can
it.
also
Okay.
attach it to them and then try. So it's just not as efficient to have a single little propeller and have attached some nano drugs, because you really need to work in higher numbers.
Okay,
Yeah.
got it.
So this situation is so desperate at the moment. So let's say 1%, less than even 1% of the drug that is taken by these patients actually accumulate within the tumor. The 99%, I mean, they are distributed in the rest of the body or just gets excreted. So
if you're successful, which I'm assuming both of you are going to be, you'll actually make a pretty profound change in the way we're able to treat tumors. You know, I mean, this is...
It is also, I mean, there are so many drugs out that would be great if they could be more effectively delivered. And so we're really trying to work on the delivery aspect.
Yeah,
that's
okay.
true.
That's really cool. I get it now. I finally get it. Another question for you, and you said was kind of curious to me, and I got to know for you. You actually attached a magnet onto the cell. I mean, how do you attach a magnet to a cell? That's like
it's molecular bonding. So bonding at the molecular level, basically. Yeah.
Okay.
So yeah,
that's a small magnet.
It's a very small magnet, smaller than a cell, but it's an effective one. So it's a powerful approach, we believe, because it's not only a magnet, so you can load other things that keep cells under control. Because these cells, once they're in the cancer, for example, so they lose some of their identity, because the cancer environment creates in such a, treacherous environment for these cells. They change their phenotype, basically, so the way they should function. But by continuously instructing cells to remain their phenotype will be a powerful approach
cool.
to tackle.
I was thinking of super glue, and it just didn't quite work.
Exactly.
Okay. And so, and I'm thinking of the other part was the magnetic fields, because you had on, there's a driving, and you talked about how you were using it, and then you're talking about we rotate. So there's something rotating around my arm. Is that how we're going to do it, or how do you rotate a magnetic field?
So you can take a magnet and rotate it, indeed, but what is a bit more elegant or makes it easier than for a more complex movement is basically you have coils, an electromagnet, and then you change the waveform of the current that goes through, basically sinusoidal waves.
Far more clever than my big magnets rotating around my arm.
That also exists, such permanent magnets, in clinics,
And so is it actually, in your mind, because you've been working on this for a while, is it something that you would actually have your body being there, you've been injected, and there's a cuff or something, or how, in your mind, from a therapeutic standpoint, I'm going to the doctor and she sits there and tells me this is what's going to happen, and your device does it. How do you imagine that's going to be?
It could be a similar system like an MRI, like a capsule where you're in and you're surrounded by coils. Yeah.
Cool. Okay. Does anyone here have a question? Okay. Go ahead. One or two. We'll take both of your questions. Go ahead and make them real loud, and then here you got a mic coming for you.
Does it work?
Yeah.
Okay,
yeah.
Perfect. We were already talking about immune response, and especially for your approach, I was interested in this. That's a very interesting idea with the iron to, get rid of the food for the cell and kill it by that. And I was thinking about if you can also kill the bacteria itself by just getting rid of the iron already. Because if you get rid of the bacteria, also the immune response will be less, I guess.
That's a very interesting point. The bacteria do just not produce magnets anymore if you take away the iron. So it doesn't kill them. They just continue to grow without magnetic response.
I see.
But it's an interesting idea. I think there will be, to control basically their growth, there will be probably also very either selective antibiotics or other solutions of, and anyways, the overall immune clearance that we then also in the end want to use for their clearance. Yeah.
Okay, thank you.
We have another question here, and then?
I have a question. You said that from your point, it could be these products could be available in like 10 years, but just like isn't it like 10 years too small of a time to like be fully see the Folgen?
Long term?
Yeah, the side effects, long-time side effects from like putting magnets into your body.
Yeah, this is a very good question. Thank you. So yeah, I mean, 5 years ago or 7 years ago when I entered the field, when this question was asked, I would say, people would not even believe that such technologies would even come into fruition one day. But now, after 7 years, we see that a lot of know-how is already there. Of course, I mean, most of the research we do at the moment is done in the lab without any real animal or human being involved, right? So, of course, when we get to that stage, so the new challenges will rise, like imaging, safety issues, and how to patients for therapeutic or diagnostic reasons. I think we will still need to wait. As I say, the same example. So the mRNA vaccine technology was available even before the pandemic, but because of the regulations, because of the approval procedure, it could not be used until such a big thing. I mean, maybe not that I'm wishing for another big catastrophe so that we can use our robots, but yeah, I think
No. Thank you. Simon.
I think one thing to add is also that because you pointed out the magnetic material also to put into the body, right? We're also building up on decades of research on some of the components. Like it's good to use something that has been already tested. For example, iron oxide nanoparticles have been used as T2-weighted MRI contrast agent or for anemia. So some of the materials we also employ on the cells is basically where we have longer term experience already.
exactly.
Yeah. Great question. Other questions? Go ahead. We got two more. I've got a whole list here, so don't worry. You don't have to scrape any barrels. Go ahead. Yep. Go ahead.
Me? Okay. This specific area of research, is this something that is very particular for your teams, or is this something that is being researched all over the world?
Great question.
All over the world. So there's really, across the globe interest in using living materials and engineering living systems for therapeutic applications. Yeah.
Yeah, it's a growing field. Right?
Yeah.
So it's, I mean, maybe 10 years ago there were only few groups, but I guess it's uniformly distributed all across the globe at the moment. Yeah.
So what has enabled this boom, if you will, in this as a research field? I mean, because you said 20 years ago, well, we saw in 1891, William was into this, but he wasn't able to model it. He just tried, right? So this is not, as you said, not brand new, but what has enabled you to be able to do this kind of work?
So,
yeah, I guess it's a kind of a convergence, right? So convergence of lots of disciplines. So I mean, there's this what we know from nanotechnology, so that we know how to make nanoparticles and work with these nanoparticles. Material science, engineering, biology. So they all come together, and then I mean, there's also this prototype of multidisciplinary researchers. So I would consider myself one of them. And so it is this type of understanding that would, I mean, because these robots don't belong to a single discipline to make, right? So you need to know multiple things from different disciplines.
Interesting.
yeah, exactly. No, it's a convergence of sciences that we experience in especially in the life science area. And I think, basically the interdisciplinary, and then also, especially also in synthetic engineering, synthetic biology. These are really now new toolkits we can use for more control, and then in combination with the engineering control.
Exactly.
Yeah.
So I can imagine like the computational capability allows you to understand and model in ways which we just couldn't do even 5 years ago, right? So I'm sure that's also helping.
It's also a point. Yeah.
So why? This is a question to both of you. Why are you doing this? What the nano, perfect entry, slow down. Why have you chosen this field?
So my passion is to increase the lifespan and the quality of the people. So this is a kind of obsession that I have, and I believe the small-scale technologies is a means towards that.
Okay. Cool. That's a good statement. You can stop with that one. That's perfect.
Perfect. Thank you.
Great.
Simone?
How can I?
Yeah, exactly. Yeah, come on, Simone. Top that one.
No, I mean, for me,
seriously.
there was indeed this fascination for the microscale. I have to say, there's as the physicist Feynman already said, there's plenty of room at the bottom. It's fascinating the kind of coming up with new engineering principles, and then using that for the purpose of basically advancing healthcare and helping diagnose and treat diseases. Just a wonderful environment to work in our
I think
application.
it's really cool. To me, for both of you, this is you must wake up, I'm sure, frustrated a lot, but what a great motivation to know you're doing something which can truly help people. That's pretty cool.
But it would be like, say, I mean, at least for myself, I'm motivated each and every day. So most
That's
of the
good.
days I'm really pessimistic, but yeah, I mean,
Come on. Hey, come on. I want you to be a pragmatic optimist. That's what. But let's say, what are some of the hurdles which you see when you're looking forward of, like the hurdles to jump? What are some of the big challenges, some of the big research questions, or we've already mentioned regulation one, but what are some of the hurdles that you're seeing?
Well, there are many
Oops.
hurdles. There's a lot also on basically. You've seen also in my talk, we use model systems. We try to first test a lot in vitro, so basically where we culture cells and try to replicate also physiologically relevant models from the human body. But there's still a lot we need to learn about the human body. So little known in the end of a lot of reactions in the human body, and that makes it very hard then to predict and how what you actually successfully show in a dish, how that then ends up actually even on an animal models, but then also later in clinics. And I think there's still so many parameters that can affect, and it's also different from person to person then in the end, right? So this kind of, we talk a lot about personalized medicine and all these factors that gonna influence how we react to a drug in general or how we behave. And I think I feel now also with big data and getting more information, hopefully will help us solve some of these puzzles also, yeah.
So for me, it's quite interesting how you're saying you take the cells from a person best. That kind of makes it more this my personalized nanobot, right? I'm saying my personalized cellborg. I feel like this can be a poster, the cellborg. Or that's a great title for a science fiction horror film or whatever. So the cyborg, the cellborg. So, but that could get to personalized medicine, and where do you see the personalization going? Is this like something which will be beyond our reach, or do you think within our professional lifetimes we're really going to see this as a personalized treatment? Right?
with robots or in general?
With robots.
Yeah. I mean, I definitely believe that this would be possible.
Yeah.
I mean, unless something very interesting happens. So I expect it before I retire. I will see and hope to. I mean, I guess we will be leading, hopefully, some of the attempts.
I wish you had it before I was retiring. That would be even better. I mean, for all of us. So I think. Any other questions here in the room or online? Here's one over here, and then we'll check online.
So first of all, thank you very much. It's very interesting. I never heard about this topic before, but I wanted to ask, like, in first place, you will use it to treat for the treatment of cancer, but what else could it be? Like, what else could this technology be used for? Like to transport for like transport other medication or even further ideas about it?
Cool, great question.
Yeah, this is a very good question. So I think I would classify it in several generations. I guess the first generation of microrobots, I don't know if you would agree, but so will be mostly about delivery, because delivery is one of the biggest problems in biomedicine at the moment. As I say, so only 1%, even less than 1% of the drug is delivered where to their right address, right? So, and this is not only cancer. There are many other diseases, for example, stroke. So, right. So, in these type of diseases, microrobots can provide real leverage. So, But afterwards, robotics. I mean, robotics is not only what we showed today. So there's also soft robotics. So there are other systems which can really contribute to tissue engineering, making new tissues. So by different means. So yeah, in my opinion, there are different areas already where we can renew tissues, organs, and then deliver drugs for different diseases. But these are mostly the physicians. I mean, I would say something a big missing at the moment is the involvement of physicians. Because it's mostly scientists and engineers that lead the field, typically, mostly. But so as we develop new concepts, so they become more and more interested in their potential applications. And then as they tell us, this could be a great application for your robot, then we develop specific prototypes there.
So Simon, what about you? What do you imagine, what else could this be used for?
Yeah, indeed. So actually we also work on some blood clot formation and how we could help there and intravascularly change the hemodynamics or help drugs get into these clotted regions. And then also we work, I didn't show this here, but we also work a lot on systems for diagnostics. So to better, because you might have some inflammation values that show up in your blood work, but that signal needs to be already pretty high to see if there's something going on. So we're trying by having intravenously injected systems that can locally resolve if something is a bit off, which you would not see with all the noise in the blood, to basically help for more preemptive medicine. So there's some work on that. And then also, I mean, with the bacteria, I have to say the specific application in cancer is because really that's the tumor environment gives them a place where they like to grow. So this is very specific for in cancer therapy. But they have been now also, for example, as a diagnostic application for bacteria that go through the gut and can record some also some signals that are off. So basically as new diagnostic tools as well. So yeah, to add that.
That's cool. That's really cool. So another question, or I'm going to ask one? Okay, I thought you had one. Thank you.
Yeah. I have two questions. The first one.
Wait. You get one, and then we'll see, okay?
Okay. Are there any cancer or tumor types which react better to the technology than others?
Yes, there's, so excellent question, so we probably get the second one.
She's right.
And this is also under exploration, so we test this in different, we see resistance with bacteria to different cancers and different reactions on that in different bacteria species, so this is an ongoing field and just understanding these interactions and there's a difference. And so that will also, there might be, and we're hoping to also identify then also which patient could respond to this therapy very well, which are the parameters. So this is an ongoing field of research, yeah.
That's a great question. Okay, well, we'll take a vote. Do you have another question? Yes, no? We're in a democracy here. Come on.
Can I take my second one?
Yeah, go ahead.
Okay. Yeah. How do you deal with people who don't understand your work or don't believe in science?
Ooh. Good thing you didn't ask that one first.
We show cool videos.
So, I mean, yeah, we try. So I'm really I think I'm engaged, or it's also what I communicate with, or do with my group at public outreach, that we have, events where people can visit our lab, or we take part in events and on ETH Zurich campus for the public. So basically trying to, as much as possible, communicate what we're doing, and hopefully in a way that it's that it comes across well. So yeah.
Very good. It is also a very good question. And I think for all of us, this is one of the reasons we're here now.
Yeah.
Right, it's in trying to help all of us understand. I mean, I didn't know much about what I've just heard, and probably you as well. So the only way we can help get over the Schwelle is to explain. And to talk. And so this is why this dialogue is so important. So it's a very good question. Thanks. So I'm going to ask one. You said you 3D printed 10 million robots.
So we can.
From 1 liter of blood, or 1
milliliter of blood.
1 milliliter
exactly.
of blood.
Yeah.
10 million.
I mean, we haven't done it.
Okay.
So if this is what you're asking, so
Yeah,
this,
it's okay.
this will take a lot of time, but so it can be done.
And so, but when I think of 3D printing, I think of a glue gun, you know, or cement. I didn't think of 3D printing at a nanoscale.
Yeah, this technology is available. Actually, it's even commercialized, so it's well developed, and
kidding.
we are developing the right material compositions based on what we want to achieve eventually. Yeah, we can use and print them.
That's incredible. You do this just.
Same
You act
system.
as if this is normal, like you have a nanobot printer. And just, okay, I didn't know about that. So, okay, just trying to imagine. So I want to come. Another question is, which I was quite fascinated by right at the very, very, very beginning, which you said, when you go down to the nanoscale, you give the fish this wonderful thing with the little fish, where in the honey or the oil, the fish was doing this and not going anywhere. Right? I'm thinking to myself, so what you're working in is a fundamentally different type of physics, or is this not different physics, or just some parts of physics which are different? So what?
It's not, I wouldn't, so I said also physics change. It's basically, we have the same equations, but other terms get more dominant as basically, which changes then, and some parts get then negligible, and that change then basically the whole effect. So you're in a different fluid dynamics regime. So for example, you would not see mixing, you know, if we have a turbulent flow, which is high Reynolds number, you, like when you open your water valve, and you would have two streams with different colors, it would immediately mix. Right now, at a very small scale, we're in a laminar flow regime, so this is where it gets basically more very viscous. It basically these streams would flow parallel to each other, and you have hardly any mixing.
Oh, really? So if we're at a nanoscale, we inject two streams, they're going to stay parallel. Yeah. But say in water, they're going to go
as in turbulent flow. And this is, and so knowing which regime you are, you're using the same equations, but you're changing basically.
What about gravity? I mean, does gravity have the same impact, or is there less impact?
Inertial forces get negligible. So as you become so small, so
gravity is irrelevant.
Yeah, irrelevant.
At some point. Interesting. Okay. I'm trying to get my head around a different physics here. So you work in a really different world, quite literally.
Yeah, this is what makes it fun, actually, right?
So what do you dream about at night?
I try not to talk here.
Okay, all right. Any other questions here in the room? Anyone have another question? Anyone online have a question? Yes.
I'm very interested in the nature of innovation and the thoughts behind it, and the role that chance plays in surprise. Has anything surprised you particularly during your research that you weren't expecting and brought you somewhere you didn't think you'd land?
Great question.
I mean, my experience is that this is often the case. So it's mostly serendipitous. So we start from A, we want to go to point B, but we usually end up in point C. The project, so we start a project because we have a goal in the beginning, right? So we discuss how we achieve that goal, but eventually, so things sometimes, the experiments don't work or show us something completely different than how our insight told. Then we take the other direction, and then, but it's within the nature of research, in my opinion, in my experience.
Yeah, I agree. There are often surprises, and also if you then look for a microscope and you observe. So I had moments of my personal Eureka Alerts where I didn't expect that response, and then I go back to the drawing board and try to understand what's going on. And once I also thought, wow, this is a new innovation. Then I realized someone else had already published on that, which also happens. But it only means it was a good idea. So.
Man, then you can build on it. I mean, that's really,
exactly.
This is a scientific process, right? So, any other questions? Go ahead. And then
I'm sorry, this might be a very stupid question, but do you see any ethical problems with like controlling bacteria or putting robots into our bodies?
This is a very great question, I have to say. I mean, ethical concerns in the sense, I guess it's more on the regulation side, really. Or, I mean, with ethics, you mean in the purpose of it is as a therapeutic application, right? And we have our, so maybe coming back to what would you find is unethical about it? Let's, if I rephrase it back to you.
So first, maybe like very super, but maybe controlling bacteria for our benefit, first of all. And second of all, putting robots that are controlled by somebody else into our bodies.
So, I mean, there is a high risk if we're talking about potential abuse or misuse of that requires, of course, ethical considerations. But overall, I think this can be, and that's why also regulations take so long, because all these aspects have to be considered. So, in that sense, I don't feel quite of an ethical concern actually about controlling of bacteria. I don't know if how.
I think it all depends on the application. If you are targeting a cancer with bacteria or robots, I really don't see any problem. But let's live in a science fiction world, and where we can really control, send the robots like mysterious, like Bill Gates chips, and then send them into the brain and then rewire the brain. If this capability would existed, then that would be an ethical problem. But other than that, this is exactly what we have when we have, I mean, how we use other medical devices, except this one is too small, we don't see them, we control remotely, and then they do their job. So realistically, I mean, if this is an experimentation again, without people knowing, or without, I mean, concerning animal welfare, everything, so that will be an ethical problem. But other than that, this is just another biomedical device that we use. Right.
At the moment.
At the moment, yeah, at the moment.
50
years later, I hope to have this conversation again. I don't know.
So this is the question of safe bacteria. That's sort of also quite interesting. Let's move forward another 30 years, right? And say, or another 130, but let's say 30 years. We're not going to go 130, but say about, let's say 20 years, 2040. You have both been successful, right? You yeah, exactly. There you go. Right, right. You get a joint Nobel Prize or two, right? And we're all going to remember the time we sat with you here in Stuttgart, and you're going to talk eloquently about how wonderful it was, you know. But no, but seriously, so we're in 2040. What has really changed when you look back at in our medical system, or when you've been successful? What has changed in the system? What are you hoping to reset?
So I believe that this microrobotic technologies in the beginning will leverage what is available. So they're not going to revolutionize everything overnight, or I mean, even in 10 years we will have most of the technology available. But what I expect is that it will leverage the existing technologies, leverage the healthcare providers. In the next 10, maybe 20 years. But real revolution will probably come afterwards, because once we are safe.
And 2041 is the revolution. Is that what you're
saying?
Yeah,
maybe.
Okay. So we're
1 year
okay.
later, yeah.
Okay.
Yeah. This is what I expect.
Simone, what about you?
Well, yeah, I think that these technologies can basically help to move to more unobtrusive, preemptive, and in the end personalized medicine. That this will become more normal, that we also have more in that sense, diagnostic systems with us to better, if you think about cancer, for example, it's not, we have system, like with a positron emission tomography, we can detect very, very small cancer lesions in the body, but it is not sustainable to put everyone every week for a PET scan. It's financially time, and we don't want to live also with the idea every week I need to get checked on that. But I think we can really, with nanotechnology, robots, micro nano systems, that we can move to more unobtrusive monitoring of health, that we earlier catch if something is going wrong and can then redirect. So this is what I'm hoping and working on to hopefully move to, yeah.
That's very cool. Well, I sincerely hope both of you are successful with this. It's been an absolute pleasure to learn from you today. Thank you for that. Really, for being inspired and for your passion, for both of you for your passion and for making time to be with us. And thank you, all of you here in the room, for coming and joining us, and those online, thank you for joining us here as we rethink living. I've had a few new words before we show the final movie, which I have to click, is the age of living machines. Right? That's an interesting one for us to think about. It might send shivers down your spine. or might give you inspiration, but to think we are now at the age of living machines as we rethink living. Magnetotactic. Did I say that right?
Mm-hmm.
Yeah.
Right, that was a word I never knew I needed to know, and that's in the Cellborg. These are my things I'm going to sort of take away and try to think and remember. So let's give him a round of applause to say thank you very much. Now, before we head over for those who are present to have a glass of wine or apfelschorle, I'm going to show you one last little movie. And you can, no, you stay here for me. You just stay here. Rethinking Living, and thank you all very, very much. Really good job.